All right, so we're going to talk about fast multipole methods today, but I wanted to try to make it a little bit broad to start with. So the problem that it addresses is actually a matrix vector product. So performing a matrix vector product which of course comes up in all sorts of applications and, you know, infinitely many problems. We have to compute a matrix vector product at some point, and it's order n squared time and memory. And when we have applications coming from really big data sets, this can be a problem with the n squared time. So one solution is the fast multipole methods. For a particularly structured dense matrix. Particularly structured dense matrix. We can reduce it to n log n or even order n time sometimes. So n log n or order n. And we can also reduce the memory too, but I won't talk about that so much today. Okay, so like I said, a matrix vector product. So let's look at V, which will be the product of a matrix phi and a vector U. And remember that when we compute this output vector V, each of the terms is actually a sum of terms from phi and terms from U. So this we could write as the sum from I equals 1 to n of, in this case I'll think of phi as a function, so of some yi, xi, and some of the terms of the vector ui. So this is where the n squared time comes from if we just compute a matrix vector product directly. So in order to get our reduced time, there are two key ideas to fast multipole methods. So the first is that we want to manipulate this sum. So manipulate the sum to approximate the solution. And then we can bound the error. So we know from classes like CS 515, and I'm sure lots of other classes, that when we're approximating the solution to a problem, as long as we can bound the error to, say, machine precision, then that approximate solution is in fact the solution we're looking for. So the fact that we have to maybe approximate this solution isn't actually a problem for the most part. Okay, so phi, like I said, it's a matrix. You can think of it as a function as well. And if we think of it that way, the entries are phi of y1, x1 across to phi of y1, x. I'll use capital N, phi of y m x1, and phi of ym, xn. So we're actually inputting two vectors. X is the vector, maybe not a vector, maybe it's just a set of points. I think either way you can think of it. So x1 through xn. Where the xi are in some real space. And then also y is the set y1 through ym, where the yj are in the same space. And phi we also call the kernel function in this context. Eraser. Okay, so I said that we can use fast multipole methods for a particularly structured dense matrix. So what exactly is the structure that it has to have? So we can use the fast multipole method when we can make a low rank approximation. So we can use fast multipole methods when we can make a low rank approximation to phi. So phi we can write as a times f. And it's either an exact low rank factorization or just an approximation. So when we can do this, here's why this can work. So here we had this sum, Vj is equal to the sum from I equals 1 to n of, let me write ui first, phi of, yeah, I'm using the same notation, although I think I made a mistake over here.
I think you just need a j.
I just need a j. This one's a j, yeah. Yeah. Yj xi. Then we can take this to its low rank approximation. So this, what do I want to say? We have the sum from I equals 1 to n, and then another sum from, oh no. This is why I typed it all up, because I can't read it. Okay, so from m equals 0 to p minus 1, another sum I equals 1 to n of ui am xi, and then our other factor fm of yj. Okay, so if each of the terms here we think of as a vector b, then computing the vector b is linear, and then computing the whole sum will also be linear, and we can reduce this. It turns out to be of order p times n plus m. So that's the idea behind it, and then I thought we could look at the Endbody problem, which we can use in a fast multipole method for. Okay, so here's the Endbody problem. Given a set X of n target points, and a set Y of n source points, they're called. A kernel function which we now change to G of xy, and then a set of weights. And we call these F. Okay, we wish to compute the potential, which turns out to just be a matrix vector product. And the potential we denote by U. Okay, so unfortunately I used U to mean the opposite vector in my earlier notation, but hopefully you're not thrown off. So it's this product of the matrix, and this time my vector is the set of weights. So the Endbody problem comes up in a lot of applications. Here are just two applications. Astrophysics, where x and y are equal and it represents the location of n stars, and the potential that you're computing is the gravitational potential. And another example is electrostatics. X and y are equal again, or they don't have to be. X and y are just the location of n charges and n probes. And we compute the Coulomb potential. And each of these has a specific kernel function, G. And this example, the Coulomb potential, is the one that I thought we could work through and see how we apply Fast Multipole method. All right, so we start with a base case. So let A and B be two disjoint squares each containing n points. Okay, so here's B and here's A. That's supposed to be a square. Oh, yeah?
You said this, you're working from the example of electrostatics? Mm-hmm. Okay, so we can think of B and A also as maybe X and Y, as you have written on the right-hand panel?
Sure.
Okay, just checking.
So two squares, and they have the same number of points. Okay, so in this base case, we want to approximate the potential in A induced by B, which is just, the potential is the U. Okay, and the traditional sense of just doing this product is n squared. So we take another route, which and there are 3 steps. So the first step is we sum the weights of B to get FB. So just summing up those weights. And place that sum at the center of B, which they call CB. Okay, so here's my new copy of B, and here's the center, CB. We sum up the weights and we put it right there. And this is a order n operation. All right, then step 2, we evaluate UA, which will just be the kernel at the center, CACB, times the thing that I just calculated, FB. So we're, yep.
Sorry, CA, I guess, is the center of...
Yes. Okay, so we're just considering the kernel function at the centers of the 2 boxes. And this is just an order 1 operation. All right, and then step 3, we use that UA approximation as the approximation of the potential at each point in A. So whatever we found is our approximation for all of the points in A. And that'll be order n again. Okay, so we get an order n approximation instead. Okay, so this, like I said, to use the fast multipole methods, we have to be able to make low rank factorizations or approximations to the kernel function. So that's what we did here. We did a rank 1 approximation. So instead of taking the kernel function on the whole space, we just used at the centers. I should use. Okay, so this is order n, so that's good. But we have some restrictions. A and B must be well separated. Separated. So well separated might mean a lot of different things, but in our case, we're going to say that A and B are well separated if the distance between A and B is at least the width of the boxes, A and B. Okay, so A and B have to be well separated. Also, what else? This doesn't quite solve the whole problem. So this problem approximated the potential of A induced by B, but in general we might just have one space and we want to calculate the potential between all pairs of points. So this, like I said, it was just kind of a base case. And then also the points must be quasi-uniformly distributed. Or maybe that comes later. No, I think that's now. Quasi. What's that? Yeah. Okay, and essentially I just mean that this approximation that I did just has to approximate each point kind of uniformly, so they need to be spread out in a nice way. Okay, so let's look at the general case then. Okay, so for the general case, so this time I use x and y. I go back to that other notation. We'll use the A and B again. And it's a set of endpoints inside a unit box. A lot of points. Okay, so what we do is we partition with a quad tree structure. Okay, so that just means that at each step, every piece gets divided into 4 new pieces. So at the start, I just have one big box, so I divide it into 4. And then I can do another step. Each piece gets divided into 4 new pieces. And you continue doing that until the leaf box, the number of points in there is sufficiently small. So you continue until the number of points in each leaf box, and we actually want it order 1, on order 1. And the tree structure means that, for instance, these 4 boxes would be like the child of this bigger box, so we keep track that way. Okay. Okay, so the algorithm actually starts at level 2. I didn't tell you what levels mean. So level 0 is the whole original box. And then at level 1 is when we have 4 boxes. So here, this is level 2, what I've drawn here. Oh, I missed one thing, I should say. So the whole tree has order log n levels, and each level has 4, reword that, level k has 4 to the k squares. So at level 0, there's 1 square. At level 2, there's 4 squares when we've done the division once. And each square has order n divided by 4 to the k points. Okay, just a little bookkeeping there. Okay, so now let me start the algorithm like I wanted to. So we start at level 2. So I have to do my division. Okay, so let B be a box in level 2, or square. So I'll pick that to be B. Then we divide the remaining boxes into B's near field and far field. Okay, so in this case, B's near field is going to be all of its neighbors, and its far field is the remaining boxes. Okay, so all of the boxes in B's far field are far enough away that we can use that 3-step process that I described earlier, right? I said that they would be far enough away if the distance between the 2 boxes was at least the width. Okay, so if A is in B's far field, we can use the 3-step process. We can use okay, so we get to take care of all those, but everything left here is too close by, and so then you just move down to level 3. So the remaining boxes are too close to process. So we move to level 3. Okay, but before I move to level 3, I just want to talk about the complexity of completing level 2. So there are 4 squared boxes because we're in level 2. And there are order 1 boxes in B's far field. So for any B, the order of 1. And there are order n divided by 4 squared points in each of the boxes. So remember, doing the 3-step process, took the order of the number of points inside the box. Okay, and then we have to do it 4 squared times, once for each of the boxes. Okay, so we get order n to compute level 2. Make sense? Okay, so then we go to level 3. So level 1, level 2, level 3. Okay, and we do the same process just about. So let me pick a box B in level 3. Then we divide again into B's near field and far field. So the near field will be all the neighbors, and the far field is everything else. But we get one extra bonus, which is that some of the points in B's far field, we've already computed the potential. So those are here. So they happen to be in B's parents' far field. We don't have to do those ones anymore. But that's pretty hard to see, but oh well. So again, any box A in the remaining pieces of B's far field, we can compute using the 3-step process, but these ones are too close to process, so we have to move down to another level. And again, the complexity is going to be really similar to the last step. So there are 4 cubed boxes in this level, and each box B has order 1 boxes that we need to compute the potential for, and the complexity will be n over 4 cubed to do each one of those. So overall we get order n again. So we just continue this process until you reach the leaf level, and when you reach the leaf level you can just compute directly the potential. Okay, so I guess each level is going to be order n. And I said before we had order log n levels. So this whole algorithm will be n log n. So an improvement over the direct computation, which was n squared. And I will say that there's a different way to compute this. You can get it order n if you just rearrange the order in which you compute things. It's not quite as intuitive as this method though. I think that's it. Any questions?
Can you say a little more about what the order n method is?
Sure. Okay, so at each of these levels, we're computing the potential between these boxes. And so it relies on, remember when I described the 3-step process, we had to compute this piece. So it relied on the fact that, for instance, this term for this box is actually the sum of 4 boxes here.
Okay.
So it would compute all these first for each level, and then those terms UA we also had to compute. It would also...
So you do the leaf level calculations first, and then construct, when you go up a level, you construct those values from just the leaf boxes?
I think for each of these, one direction you start with the leaf level, and the other direction you start at the top.
Oh, okay. Gotcha.
So you're computing values, not necessarily the ones that go together at that time.